So in this video, we're going to start with chapter 17, in which we apply Newton's equations to rigid bodies. So the first thing that we need to look at is the definition of moment of inertia. Moment of inertia is going to play a key role, and it's going to be the equivalent of mass in the equation of motion for rigid bodies. So let's assume we have a rigid body, like here we have this blue potato, and then we want to rotate this rigid body about this axis z. So, and we want to be able to describe this using an equation similar to Newton's second law. So now, so we want to do that. So this axis goes about the center of mass, is free to rotate, and then what we are going to see is that the equivalent to Newton's equation, and I'm going to write here, this is Newton's equation, F equals ma, is that the moment is equal to the moment of inertia times the angular acceleration. So as you can see, this quantity here, I, that we call the mass moment of inertia, plays a role of the mass. What does the mass do? The mass is somehow a measure of the resistance that a body has when it's being accelerated. The heavier the body, the more force you have to apply to get the same acceleration, right? So for rotation, then the more moment of inertia that you have, the more moment torque that you have to apply to get a given angular acceleration. That's the idea. It's a property that measures the resistance of a body to angular acceleration. So, so then let's look at the definition, and we're going to start with a very simple model, and then so to remind ourselves, we have a dumbbell here. Let's say this is mass m and mass m, and let's say this distance is r. So what is the moment of inertia of this system of two masses? Well, the definition is this: the moment of inertia I is going to be equal to the mass times the distance squared. And then you're going to add over all the masses in the system. So in this case, we would have 2m r squared. This is the moment of inertia of this dumbbell. So things to remember: the more mass you have, the higher the moment of inertia. That means the more torque you have to apply to get a rotation about this axis. The farther the objects are, the higher r is. The greater this r distance is, so the more the moment of inertia. So those are the key important quantities here. So how do we calculate moments of inertia? Well, we are going to use integration. So the idea is that you're going to have an axis here, and then you want to calculate the moment of inertia about that axis, and it's always calculated about that axis. So you're going to break the object into little pieces. For each piece, you're going to calculate the perpendicular distance to the axis, and then you're going to add over all those distances. When you do that, you get this integral here, and that is called the mass moments of inertia. The units are kilogram meter squares or slug feet square in British units. So let's look at some moments of inertia. So we have a disk and a square. So you can see I can rotate the disk about this x-axis. If I did that, then this would be the moment of inertia, and is 1/4 mr squared. I can calculate that using integration. And by symmetry, you can see that rotating the disk about the x-axis is similar to rotating the disk about the y-axis. So these two numbers are the same. Rotating the disk about the z-axis, that is 1/2 mr squared. You can calculate that using integration. And rotating the disk about this point here, and this is what we are going to use when we look at wheels. So rotating the disk is 3/2 mr squared. So these are numbers that are good to keep in mind because they are going to appear a lot when we look at wheels and pulleys. So here we have a square, and again we have rotation about z-axis and y-axis, and they are the same, 112, right? Except that of course we could have b and a be different here, but the form is the same. About the z-axis is 112, but now you have a squared plus b squared. So when we want to calculate moments of inertia, what do? We have to do an integration. And in most problems in this book, you're going to have a very nice symmetry, so you can use either shell elements or disk elements. So basically, you're going to write the moment of inertia for one of these elements, and then you're going to add and do an integration over the whole system. So that's all you need to do. So we're going to see some examples pretty soon. There is an important theorem here. So in some problems, you're going to need to find the moment of inertia about a generic axis that is parallel to an axis that goes through the center of mass. So if that is the case, then let's say I want to find the moment of inertia about this z-axis here that is parallel to this z prime axis that goes through the center of mass. If I know the moment of inertia I prime about this axis, then the moment of inertia about this axis is equal to I prime plus the mass of the object times its distance squared. That's all the parallel axis theorem says. The demonstrations is in the book. Yes, it's very simple. Just read that and let me know if you have any problems. We can discuss it. So an important quantity that appears a lot is the radius of gyration. So the moment of inertia of an object can be written as the mass times some quantity k squared. This is kind of an average distance, and then you can, if you know the moment of inertia, you can calculate k by taking the square root of I over m. That's an important quantity. And if we have the moment of inertia of bodies that are made of a few parts, like for instance, you can have something like this, then you calculate the moment of inertia of this, the moment of inertia of this, and then you add those parts. Or you can look these moments of inertia in a book, and then you algebraically add those parts. The only thing you need to figure out is the axis, because now you're going to have all about the same axis. And we are going to look at one problem. So let's start with example here. So we have this object here, and then you're given the density, and then you're asked to calculate the mass moment of inertia of this body about the y-axis, about this axis here, this red axis. So how do we do that? Well, we need to find a very nice element. So here a disk would be the easiest. Remember, the moment of inertia of a disk is 1/2 m r squared. So how do we do this? So this is the moment of inertia of a disk, 1/2 m r squared. So we are going to write the moment of inertia of a differential element that has the shape of a disk, right? So it's 1/2, has a differential mass, and then the distance is x squared, which is the radius, right? So that distance x here, right? So that's going to be the radius. And now, so we can do dm, the mass is rho times dv. So it's rho time, what is dv? Well, it's pi r squared or x squared times the width, which is dy. And now we can write the integral. So the integral is the sum of the moment of inertia of all the disks when I integrate from 0 all the way here, right? So if I write that integral, right? So the integral from 0 to 1 of d iy, right? And so on diy is, so diy is equal to 1/2 dm, which is rho dv, right? X squared, and dv is this quantity here, so that's why you get this x to the fourth here. So this is a very simple integral, and then you get this value here for the moment of inertia. So here we have another example. This is a pendulum, and it is made up of two pieces, right? So here we have to calculate the moment of inertia of each one of these pieces and add them. This is a composite body. So how do we do this? Well, we first get the moment of inertia of this piece here, and then we need to write it about this O, and the moment of inertia of this piece, and we need to write it about this O. So in both cases, we need to apply the parallel axis theorem, right? So in both cases, and then so that's all you need to do. So you can find the moment of inertia of this piece on a table, right? So that is this IG here, and the moment of inertia of this guy about the center of mass here, right? And then you basically then apply the parallel axis theorem to both, right here and here, and then you get these two numbers, and then you add the two numbers, and you get the moment of inertia of this piece about O.